Jeroen. I will focus on what Rob asked me to do after almost 15 years in research, trying to make it finally into industry. And so I will focus on this part. But before going, I want to address, or I want to introduce this framework that I find extremely useful by my colleague Catherine. This is focusing on the embodied emissions and very clearly shows the three main levers that we want to try to address. So it's not just about using better materials. Equally important is using less. And then lastly, and increasingly important, because that addresses the problems of the next generation, is to try to keep resources, components, buildings as much in the loop, and that is where circularity comes in. So our group has been looking at this through these three concepts, so strength through geometry, material effectiveness, so not just efficiency, but really using the materials in the correct way. It's not just about lighter if you use very high embodied emitting materials. And then lastly, this is a general term, but I will show you how we approach things really also offers circularity. So strength through geometry first. For those of you who know our work, I did actually my PhD on assessing historic structures in masonry. These are amazing structures, and the more that I was doing this engineering research, I appreciated that we might have lost some key knowledge. So in 2016, we built this armadillo vault to kind of bring to our community to clarify the strength and the beauty of geometry. What you're looking at are 399 pieces of cut stone held together by its shape, so no glue, no mortar, no reinforcement, dry assembled by our expert colleagues from the Escobedo group. And so this statement was beyond an aesthetic one, was really one to clarify that perhaps we should reintroduce structural geometry. I care about structural geometry because, I mean, this is a bit of an abstract pavilion, but you see very clearly with this 4 centimeters of unreinforced stone being balanced in space that we can significantly reduce mass. Another old project that I show as a framing in the beginning, why I care about structural geometry. I was lucky to be involved in this project. Peter Rich Architects, John Oxendorf, Michael Ramage were the key people here. I did the engineering, the assessment of these vaults. In this case, we are talking about using local resources. So this is local soil with only 7% of cement to stabilize it, not fired, so just air dried. And also local labor. So these are local carpenters, farmers that were introduced in this style vaulting technique. Of course, here in New York City, we have many of these beautiful examples by the Guastavinos throughout. For example, the Whispering Gallery in Grand Central Station. But why I show you this older project, so this finished in 2008, is the contrast between these two images. On the right, the tiles are designed to only take 2 megapascals in compression, so that is 10, 15 times less than a standard concrete in compression. But these tiles are so weak in bending that you can just break them in your hand. So in very small packages, very careful, they're brought on site. But then on the left, you see that if you place this material that we would absolutely not consider structural nowadays, where naturally the forces flow in compression, then you see that this is indeed the proper material, a robust system, and the permanent structure. So how this works is that an arch is good for a certain loading case. If you don't have double curvature to take live loads, then you need to do something like adding a stiffener to provide load paths for these compression flows. And then if you add a tension tie to take the horizontal thrust, what we just did in the last 20 seconds is develop an alternative for a typical reinforced concrete flat plate or beam, but one that uses at least 70% less material, right? So that is indeed then nice that we can, again, reduce mass. But what's interesting here is that for these very thin sections, the stresses are so low that we can activate this low strength, low embodied carbon footprint material, because that's almost always a one-to-one relationship, how strong a material needs to be and how much it emits. So those are, for me, the two key fundamental reasons. Already 2 aspects, 2 of the 3 bubbles have been addressed with this, that we want to reintroduce structural geometry, specifically funicular forms, so compression-only geometry, to reduce mass and to reduce carbon. We will be many more people on this planet. You have heard this many times. Surely here appropriate is then to do related to New York City, right? This is a calculation of Bill and Melinda Gates in 2019. In order to provide adequate housing, infrastructure, and so on for all these people, we will have to build the equivalent of one New York City every month for the next 40 years. That's a daunting task, and hopefully we do it a little bit different than this, but this is also a reality that we live in denser environments. So to me, this was mind-blowing, shocking even as a structural designer to learn that in these medium high-rise construction, on average, you have roughly 3/4 of the mass is in the structure, so crazy situation, very different than the chair you're sitting on. The structure is much, much heavier than the users and everything that matters in the building. If you then zoom in, then you will see that more than half of that structural mass is typically in the floors. By the way, intuitively, that makes sense. Gravity comes down, columns are vertical. We have decades of research in really optimizing bracing systems, and then I showed you that naturally the forces would want to flow to the supports like an arch, and then you have this very thin straight element. And so that clash between the natural flow and your geometry is basically one of the key reasons why we have this bottleneck really in this most banal element of floor that we need to work on. So again, let's try to rethink the floor because we'll have to be building a lot of them. In fact, more than 200 billion square meters are expected to be built globally in the next 30 years. So talking about material effectiveness and maybe the gray elephant in the room, because I will be talking about concrete. I am convinced that if you do concrete right, and maybe you will have the same conclusion after my talk, that concrete is the most scalable and sustainable material to take this challenge. But another thing that we do know, of course, is that concrete has quite a lot of impact. But is it right to just say that concrete is the most evil material on planet Earth? So there's some hints, and you could say, but here you're comparing per unit mass. But so you see where concrete is on the bottom. It performs extremely well on embodied energy and embodied emissions per unit mass. You could say, let's use another performance criteria. That's not my point here. My point is just that it is really much more complicated than just looking at the material. And you probably see where I'm going with this. I consider concrete as an artificial stone, meaning a material that is happy in compression, not in tension. So the natural geometry for concrete is actually the natural geometries that have been used and developed for centuries to build these structures in pure stone, unreinforced stone indeed. And to be more precise, earlier I focused on the mass, on the volume, but just by not forcing a material to be in a geometry it doesn't want to be, but by reintroducing the stiffened tight arch, you save from a structural point of view 70% of concrete, 90% of steel. This is literally not rocket science. You can calculate this yourself. This is just physics. So, but this is what we get, right, by actually starting to embrace geometry again. So that is what we then did. So this simple arch becomes a 3D vault. The simple stiff diaphragm walls as stiffeners become stiffeners that accumulate to the corners, so that just at the corners we can resolve that inequilibrium, this horizontal thrusting, for example, with a very simple tension tie. So in this crazy building that shouts loudly, look at me, then you go look at it, and then you learn about our floor. So it is the first, many of my projects last only a couple of months, and then they're taken down or destroyed because they're pavilions or exhibition pieces. So this is actually a building that is still there. So you can go visit it when you're in Zurich. It's the first time that we built one of those floors, except for the African projects. Here, roughly 5 by 5 meter spans. And what's maybe interesting is that the structural thickness of this floor is, by the way, also a low-strength concrete. It has more than 50% recycled content, both on the cement and the aggregate side. This was very remarkable for a project designed in 2014. Here, the structural thickness is only 3 centimeters, right? This is how it looks like, and so for us, exciting and total surprise to me, actually, that we did so many crazy things, so many convincing tests in the lab and pavilions, and I would say what we did in Venice with this crazy stone vault is still, I can believe that I dare to do something like that. with more than 500,000 people walking under it, including very important people. But this project, really started to draw some attention, and so in Switzerland has given us some opportunities to start to scale this up. Let's zoom out again and let's look at these buildings to clarify what really the potential could be just beyond this local innovation. So if you take any of these buildings, so let's say about 25 stories tall, what would happen when we replace our typical reinforced concrete floor plate with the system or the approach that I've been talking about here? So as we already covered, more than 40% of the weight will be in the floor, and then you can have these savings. You see that in this case, it's not 70% and 90% because probably you need a 90-minute fire rating for your floors. There's some additional acoustical requirements and so on. There's many strategies to deal with this, but so we add a bit more material to be a bit more realistic. These are actually real numbers based on projects we're doing right now, by the way. So if you were to do this for this one building, you would save 7,500 cubic meters of concrete, right? If that is abstract, that is more than 1,200 concrete trucks that would not have to go to this one building. By the way, I'm only calculating the savings on the floors, not the savings you would have on the columns, on the foundations, and so on, right? So I'm only calculating this. So for a 25-story building, this is what you get. But also per story, you would save about 20 kilometers of 12 millimeter diameter reinforcement steel. And that coincidentally rolls out from Zurich, where I happily live and work, to Brussels, where I'm very proudly from. I quickly calculated earlier, it's also twice the distance from New York to Boston, just to give you again a sense how much steel you would be saving, reinforcement steel you would be saving in this just one building. All right, in the beginning I said like, okay, it's not just about the materials, but it's also not just about the volumes. What really matters is actually the combination between the two, the mass. Can I see how the timer? Yeah, you have to show it at me? Okay, all right. The mass, but also the impact of the materials that you use. So for example, you could use what is called the embodied carbon coefficients that you can calculate for these materials. So you take all the parts of your building, and then I will focus now on the structural bits on the floor, and then you add their contributions. So what I said in the beginning is, so remember the armadillo fault structural geometry directly addresses the mass, but also actually already addresses the embodied carbon coefficients, because in these funicular geometries, because of the alignment of your structure to your natural flow of forces, you don't design for peak stresses like you would have in beams. So you have actually nicely utilized kind of sections, and that is why we can also start to address the embodied carbon coefficient. And then, of course, I will not be using your SEM1 or OPC concretes, but I will be using state-of-the-art concretes that are now on the market. So let's see, when we break this down, how this all comes together. So structural geometry gives you two things at the same time. As said, you have the direct cut in mass, but then at the same time, you can go to a lower strength concrete. And for example, by going from a standard C30 concrete to a C16, so an extremely low strength concrete, you cut an additional 20% just by that move. And then state-of-the-art SEM3, A, B, whatever is available in your market, concretes have an additional reduction on the level of the material of another 2/3. That is, of course, by replacing clinker with other kind of waste streams or construction demolition waste, end. So that means that on the concrete level, we have a reduction not of 60%, but of 90% by having all these different aspects. The steel, we just say that we don't have electrified steel, recycled steel yet, so we use the same steel. So that means that today, when we do our projects, we can show that we have a reduction of 85%, right? So we are left with around 15–20% of the global warming potential compared to your flat slab. So here, just to drive the point home a little bit more of what I am fighting against all the time is this narrative that, we need to use a green concrete. Look what happens there. So a green concrete, by the way, also comes typically at at a premium. It depends on the market, but it typically comes at a premium. So then you can get at best a 50% reduction of the global warming potential. Not bad, it will be much more expensive, plus the mass is exactly the same. What we are doing here is also reducing the mass. And in fact, the mass that we hit is exactly the mass that is needed for acoustical performance. It's always the given mass that we need to hit, and so that is about 1/3 of the mass of your typical reinforced concrete. So here, what I show here is that if you don't use a state-of-the-art green concrete, but your most polluting concrete that is locally available, then you still save 80% of global warming potential. Just to clarify that actually the key driver is design and not the materials. Of course, it's connected because the design that we do is the right design for the materials that we've chosen to kind of push forward here. Another thing to point out is that because it's lighter, and this for me is a great kind of opportunity because we always talk about a green premium. We take for granted that a sustainable solution is more expensive than a standard solution. Here, because we don't just push on materials, but we really look at the system, this weight savings gives us so much benefits and savings on the columns, on the foundations, that in all the projects that we have done, if they are large enough in scale, so for example, only 10 stories tall, then you already can offer this innovation, these sustainability targets, cost neutral to the client, right? And that is where it gets exciting, that actually they pay much more for this floor, but in the total of the building, it's the same cost. All right, then lastly, circular construction. So the floor that triggered this industry interest was a one-off because we were already pushing enough, I think, 3 centimeters, low-strength concrete and so on. And so that is why we now develop a precast system that can very quickly and easily be assembled. It's called the Ripman floor system. So many of the things that I talked about are coming together, plus the prefabrication is added to not only be very precise, but also very quick and easy to assemble. By the way, we do full dry assembly, so that the elements can be taken apart as easily as they come together. We use low-strength concrete, so believe it or not, but these 6 meter, 8 meters, 10 meter span floors that we have built are all with C16 concrete, fully unreinforced. So we are using these low carbon materials. We do clean material separation so that we don't have issues with corrosion of embedded reinforcement. That's more for outdoor applications. But in general, you have a happy material that does exactly what it wants to do, and we don't have to fight carbonation that would attack the reinforcement, so we can have this element return to its natural state more and more and more. So that then also addresses durability. What's also interesting here is because we are extremely diligent and no compromise on keeping all materials, all components separated, so that if there is no reuse scenario or case study to be made, that we have easy recycling, clean deconstruction instead of messy demolition. All right, so this was a very early one done by Matthias in 2016. But now we were happily forced to set up an ETH spin-off to produce and deliver the projects that are now in full swing. This is called, I think, appropriately Volta. This is a video of a full-scale mock-up that we have done for a project Creatar in Zug. In fact, next Friday, the client will make its final decision if this goes forward like this, but knock on wood, fingers crossed, it's looking rather good. So that would mean our first project of over 7,000 square meters of Ripman floors being assembled. So as you saw, these were some snapshots of the building site. It comes very neatly, dry assembled together with very simple scaffolding props, lifting devices that we developed. So here, this is we're still doing iterations. In every single project, we learn something new to do it better. But what Volta does is we do the fabrication, we assist the architects for integration of systems, the engineers for the structural modeling, and then the contractors, we deliver the entire kit, the lifting kit, the assembly, the steps to be, how to do it, and so on. To give you a sense, this is a 6 by 6 meter floor, and we assembled this in less than 2 hours. So here you see Tom My right, so that's the other co-director of the BRG, my partner in crime in everything. I have a nice anecdote here, but I'm running out of time, so I'm not going to talk about this one. Yeah. Well, okay, maybe then quickly, because to me this was nice. This guy was specifically hired by the contractor as an expert, more than 30 years of construction expertise in prefab assembly and so on. And he just did not want to hear us tell him how it should be done. And so this was a great experience because they messed around for an entire day. They went back and forth, nothing worked. And so at the end of the day, he had to admit that he should have started and listened to us and that it would have been done indeed in 2 hours. Why I like this anecdote is because there's so many of these things that I can say about the resistance and the things that we need to overcome in practice. And this was the best scenario, right? Because if we would have said, no, you're doing it like this, and anything would have gone wrong, then we would have lost credibility. So this is the better way to actually have the old-timers saying what direction it needs to go and then realize that these young academics indeed maybe know what they're talking about. So here, these elements nicely come together. Again, they're fully unreinforced, right? This is nice. This is the load test. So we did 500 kilograms per square meter. Nicely much, I think about 10 times the ULS requirements. And absolutely nothing, less than 1 millimeter of deflection because of this extremely stiff shell. This looks very nice. It's a bit like the historical kind of load test, and then we gave these like little swimming pools to all the workers to take home to their families. Anyway, because it always comes up, yes, of course, it's fire safe. In this specific case, we use the structural layers, so there's different things, fire resistance, gradient insulation. We do fire tests. We have to always pay for external consultants as well. It's super expensive, super difficult to kind of get this on the market, but fair enough, we're doing something very different than typical floors. Another big, because we're so light, acoustics, and there what's neat is that you can really tune it. So you can do the bare structure and then start to add depending on the requirements of the client and how much acoustical performance they want. So this is how it looks from the bottom with the acoustical panels as infill. This is not for the vibroacoustics, the transfer of noise, but this is for room acoustical reasons. And then this, even though I stretched it here, but it looks very neat. This is prefab, architectural concrete. So this is actually all embedded in the molds that Volta delivers. So this is the one that hopefully gets going. It was a competition won with Gigon Gouillard. And as you can see, the design was entirely around the floors. Maybe a comment, I don't show the details, and I'm totally impressed by what I've seen in earlier presentations, but maybe you know that we do everything with Compass. Everyone at ETH now does everything, all developments in Compass, fully open source computational framework. And then maybe a small hint, Lee asked me not to publicize too much, but Compass IFC is coming out, which bridges and connects 100% robustly the entire Compass world to the entire BIM world. And that is also what we use in practice. So for us, open source is super important because it allows actually 15 years of experience of tens and tens of researchers to now be ready directly today and to be able to interface with our fabricators, our contractors, our engineers, our architects instantly, right? So all of this, all these configurators in the background, it's obvious for us that that needs to be done in a very robust way. So we also integrate systems so that we don't lose any floor to height kind of. Again, I'm excited about that we are starting to have success because we have a big challenge. 40% of the mass is in all of the floors of these buildings. Our approach doesn't also result in this after at the end of the lifetime. And what I've been talking about works for any compression material, but I want to have impact. So this is, for example, a 3D printed marble dust. Would also work, would be spectacular sustainability, but I'm seeing already the skepticism of the industry, or the resistance, not skepticism, we have to just demonstrate it. Let's do it first with a material that is available globally, and if you use this material in the right way, then we beat every other system. I forgot that slide, we really beat all of them. So I talked about structural geometry to reduce mass, the right geometry for the materials. For masonry, that means funicular form, so compression only, that allows to reduce emissions. I didn't talk too much, we use digital fabrication, but it is essential to optimize actually the molds, to realize these geometries also economically. Then we have to integrate our system to enhance productivity. And I mainly focus today on my strong belief that the combination of discrete masonry for unreinforced concrete, that offers all kinds of circularity opportunities from longevity, reduction, reuse, recycling, end. So that's it. That was the group at the time. So for those of you who maybe knew or wonder why we don't call it a RIP system, but a Ripman floor system. So our colleague Matthias Ripman sadly passed away 3.5 years ago. And so in his honor, we kind of call this system the Ripman floor system, because the beautiful 3D printed one that you saw was the one that he generated for the Biennale. With that, thanks a lot for your attention, and looking forward to this discussion.